Making a language model bigger does not automatically make it better at doing what you actually asked. You can scale up to hundreds of billions of parameters and still get a model that confidently makes up facts, ignores parts of your instruction, or produces text that is biased or toxic. This disconnect between raw capability and useful behavior is the puzzle at the heart of the paper we're going to walk through today, which introduces a model called InstructGPT and the now famous technique behind it, reinforcement learning from human feedback, or RLHF. To understand why this matters, think about what a model like GPT-3 was actually trained to do. Its objective was simple. Given some text from the internet, predict the next word. That's it. The model becomes extraordinarily good at continuing arbitrary web text. But when a user types, "explain quantum entanglement" to a curious 8-year-old, they don't want the most statistically likely continuation of that string on the internet, which might be a list of similar homework prompts or an SEO spammed article. They want the model to actually fulfill their intent. The authors call this gap misalignment, and they break the desired behavior into 3 properties: helpful, honest, and harmless. The model should try to do what you asked, shouldn't fabricate, and shouldn't cause harm. Before this work, the dominant approach to bridging this gap was something like FLAN or T0, where you'd fine-tune the model on a big collection of public natural language processing datasets, each rewritten with an instruction-style prompt. Think of it as showing the model thousands of examples of "here is an instruction, here is the right answer," drawn from things like question-answering benchmarks, summarization datasets, and translation pairs. This helps, but the authors argue it falls short because public datasets cover a narrow slice of what real users actually ask. Real prompts skew heavily toward open-ended generation, brainstorming, and rewriting, while public benchmarks emphasize classification and extractive question answering. So here's the alternative the authors propose: a 3-stage pipeline. Stage 1, supervised fine-tuning. They hire about 40 contractors, give them prompts collected from the OpenAI API, along with prompts the labelers wrote themselves, and ask them to write the ideal response. They then fine-tune GPT-3 on these roughly 13,000 demonstration examples using standard supervised learning. This alone gives you a much more instruction-following model, called the SFT model. Stage 2 is where things get interesting. Rather than asking humans to write perfect responses, which is slow and expensive, they ask humans to compare responses. The SFT model generates between 4 and 9 candidate completions for a prompt, and a labeler ranks them from best to worst. From these rankings, they train a separate model called the reward model, which takes a prompt and a response and outputs a single number, a scalar score representing how much a human would likely prefer that response. The reward model is trained with what's essentially a pairwise ranking loss. For every pair of responses where a human preferred one over the other, the model is pushed to give the preferred one a higher score, with the magnitude of the difference interpreted as the log odds that a human would pick it. A clever efficiency trick here is that they batch all the pairwise comparisons from a single prompt together, which both saves compute and, perhaps surprisingly, prevents overfitting that would happen if you shuffled the pairs into one giant dataset. Stage 3 uses that reward model as a stand-in for human judgment, and now you can do reinforcement learning. Think of the reward model as a tireless human critic that can score millions of responses for free. The policy being optimized is the language model itself, and they use proximal policy optimization, or PPO, to update it so that its outputs score higher according to the reward model. 2 design choices matter here. First, they add a penalty term that punishes the model whenever its output probabilities drift too far from the original supervised model. This is measured using KL divergence, essentially a statistical distance between probability distributions, and it acts as a leash, preventing the model from finding weird adversarial outputs that fool the reward model but look nothing like natural language. Second, and this is the key fix for what they call the alignment tax, they mix in a small fraction of the original pre-training objective during RL. Without this, the model gets so focused on pleasing the reward model that it forgets how to do standard tasks like reading comprehension on Squad or translation. With it, you preserve general capability while still gaining the alignment benefits. They call this variant PPO-PTX, and it's the model they refer to as InstructGPT. The results are striking. The headline finding is that the 1.3 billion parameter InstructGPT model produces outputs that human labelers prefer over the 175 billion parameter GPT-3, a model more than 100 times larger. When you compare the same-sized 175 billion InstructGPT against 175 billion GPT-3, labelers prefer InstructGPT 85% of the time. On the Truthful QA benchmark, InstructGPT generates truthful and informative answers roughly twice as often as GPT-3. On closed-domain tasks, where the model shouldn't invent information, hallucination rates drop from 41% to 21%. Toxicity, when measured with a respectful prompt, drops by about 25%. Importantly, these gains generalize to held-out labelers who never produce training data, suggesting the model isn't just memorizing the quirks of 40 specific people. And there's an intriguing qualitative result. InstructGPT follows instructions in non-English languages and answers questions about code, despite both being almost absent from the fine-tuning data, hinting that the concept of following instructions itself transfers across domains. That said, the authors are admirably honest about the limitations. InstructGPT still makes confident mistakes. It accepts false premises and questions and runs with them. It overhedges, refusing to commit to obvious answers. Improvements on bias benchmarks, like win-a-gender and Cross pairs, are essentially nil, and when explicitly prompted to be toxic, InstructGPT is actually more toxic than GPT-3 because it follows instructions better. There's also a deep question the authors flag about who the model is aligned to. The labelers are mostly English-speaking contractors in the US and Southeast Asia. The instructions for labeling were written by OpenAI researchers, and the prompts come from a narrow slice of API customers. So when they say aligned with human intent, what they really mean is aligned with a specific group of humans interpreting a specific set of guidelines, which is a far cry from aligning to humanity broadly. Now let's walk through some questions you might have after hearing all of this. First, why bother with a reward model at all? Why not just keep doing supervised fine-tuning with more and more human demonstrations? The honest answer is that human comparisons are dramatically cheaper than human demonstrations. Writing a great response to a complex prompt might take a labeler 10 minutes, but ranking 4 model-generated responses takes maybe 1 minute. Once you have a reward model trained on those rankings, you can effectively generate unlimited supervision signal by sampling new outputs and scoring them. It's a way of amplifying a fixed budget of human attention into something that can drive millions of gradient updates. Second, what's actually going on with the KL penalty during reinforcement learning, and why is it so important? The reward model is imperfect. It's a model trained on a finite dataset, and like any model, it has blind spots. If you let PPO optimize against it without constraint, the language model will find weird outputs that score absurdly high on the reward model, but are gibberish or exploit specific quirks. The KL penalty anchors the model to the distribution of the supervised baseline, so it can only move into regions of output space that still look like reasonable language. It's a regularizer that says, improve, but don't go off the rails. Third, what's the alignment tax, and why does mixing in pre-training gradients fix it? When you fine-tune heavily on human preference data, the model gets really good at the kinds of prompts labelers see, but starts forgetting some of its broad capabilities. things like reading comprehension on Squad or French to English translation. That degradation is the alignment tax, the cost paid in raw capability for being better aligned. The fix is surprisingly simple. During the RL phase, periodically take a gradient step on the original next word prediction objective using pre-training data. This keeps the model's general language abilities sharp, while the human feedback updates push it toward better instruction following. It's basically continual learning to prevent catastrophic forgetting of the original skill set. For those of us thinking about large-scale recommendation systems, there's a lot here that translates directly. The core insight that you can train a cheap proxy model on human comparison data and then use it to drive policy optimization at scale maps almost perfectly onto ranking. In a recommender, your offline metrics like click-through rate or watch time are themselves proxies for what users actually want, and they're famously gameable. You could imagine using rater comparisons or even implicit signals from power users to train a preference model over candidate slates, then using that model as a reward signal to fine-tune a ranking policy with something like PPO, with a KL anchor keeping you close to your production model so you don't ship something erratic. The alignment tax lesson is particularly relevant. Production ranking systems almost always face this trade-off. When you optimize hard for one objective, like engagement, you degrade others, like long-term satisfaction or content diversity. The pre-training mix trick suggests a clean recipe, namely, interleaving updates against your new objective with updates that preserve performance on the metrics you don't want to regress on. And the finding that a much smaller aligned model can beat a much larger unaligned one is a reminder that for serving constraints, where every millisecond and every parameter costs real money at billion-user scale, investing in better training signal can be far more cost-effective than scaling up the model itself.